Welcome back to In Depth with Academia. I'm Richard Price, CEO of Academia.edu, and today I'm talking about a paper by David Lush called Quantum Wave Mechanics as the Magnetic Interaction of Dirac Particles. Woo, what a title, right? But don't worry, I'm going to break it down so it actually makes sense and, more importantly, relate it to you, the listener. And just a quick reminder, my job here is to summarize and discuss the research neutrally. I'm not endorsing any particular view or result I present. I'm just here to pull apart the ideas and lay them out, conversationally, quirks and all. Right? So, let's start with the big question the paper tackles. What's the core problem here? That central quantum mechanics is full of mysteries, but one especially weird part is why quantum particles, like electrons, seem to behave as both particles and waves. If you've heard of the famous double slit experiment, you know what I mean. Why do we have to have this weird wave function thing, sort of a probability field, governing how these particles act? Could that actually arise maybe from something more classical, like electromagnetic interactions between spinning charges? That's the bold idea at the heart of this paper. Why is this important? Well, if there's a way to reconstruct quantum behavior from something a little more down to earth, from like just charges whizzing around and interacting electromagnetically, it could change how we understand the bridge between quantum physics and classical physics. It doesn't mean quantum mechanics is wrong, but it suggests that maybe what looks strange could have a classical underpinning. That's a fascinating possibility, right? All right, let's dig a bit deeper. The paper by David Lush builds on the idea that elementary particles, like electrons, might be modeled as little point charges moving in tight, really fast circles. This involves something called Zitterbewegung, a jittery, ultra-fast motion predicted by the Dirac equation for electrons. Here, the internal circular motion, at nearly the speed of light no less, gives the particle its spin. Now, what the author does is he looks at how two such Dirac particles would interact, not just electrically, but magnetically. And the key result, if you consider the magnetic force between these rapidly circulating charges, and here's the twist, you allow for time-symmetric electromagnetic interactions, meaning you let the future as well as the past influence the force. You get a force that isn't just static or simple. Instead, it's modulated. It oscillates in a way that mathematically resembles the quantum wave function. Let me pause for a second. That's a weird notion. Time-symmetric forces. Isn't causality important? Well, in certain formulations, like the Wheeler-Feynman absorber theory, it's legit to consider both advanced and retarded waves. Basically, you include influence running both forwards and backwards in time, which is definitely not something your high school physics teacher covered. Getting back on track, Lush finds that under these assumptions, the modulation of the magnetic force between these zeta particles solves an equation that's almost the same as the Schroedinger equation, the central equation of quantum mechanics. There's a catch, though. When you work through standard relativity, it's not an exact match. There's a factor of 2 difference. But if you use a modified version of the relativity energy formula, as some alternative theories suggest, the modulation fits the regular Schrodinger equation exactly. What does this mean for you? Well, for one, it challenges the notion that all quantum weirdness is irreducibly random or disconnected from classical physics, and more practically, it suggests that quantum wave functions might, in some sense, arise from the underlying electromagnetic dance of matter's tiniest parts. If you're studying physics or just love science, this is one way to see wave functions as representing actual patterns in the story of moving charges, not just mathematical abstractions. Quick digression, this reminds me of how sometimes if you stare at a ceiling fan spinning really fast and a light flickers at just the right speed, it looks like the fan is standing still or even spinning backwards. Your brain thinks it's seeing something real, but it's just an artifact of overlapping patterns. Is quantum weirdness like that? Patterns that emerge from complicated underlying cycles? I don't know, but it's an interesting visual. So, zooming out, the methods in the paper are, honestly, pretty technical. Modeling charges as spinning at the speed of light, using equations from both classical electromagnetism and quantum mechanics, and doing some non-trivial math to link force modulations to equations like Schrodinger's. But the upshot is a set of equations showing the weirdness of quantum mechanics might map, under the right lens, onto plain old magnetic interactions between spinning charges. Of course, there are limitations. This approach so far works best for particles with the same mass and aligned spin, and it's definitely not the last word on quantum theory. The author notes that this is a starting point, and again, I am just describing a perspective, not endorsing it. Science thrives on these creative attempts to see familiar things in a new light. So, there you go. If you've ever wondered whether quantum mechanics could emerge from deeper classical processes, this paper is one attempt at that explanation. What matters for you is to remember, scientific papers aren't pronouncements of truth, but invitations to ask, could this picture be meaningful? Could it explain something I see in experiments? That curiosity is at the heart of science. Thanks for listening to In Depth with Academia. I've been Richard Price, and as always, keep questioning, keep exploring, and above all, stay curious. Let's meet again soon. Who knows what other surprising connections we'll discover?